Hello and welcome to our senior design project, the Autonomous Crab Car, developed for Clemson University's Computer and Electrical Engineering Senior Design Program. We will begin by taking a look at the project from a broad sense. The vehicle, developed by combining the uses of both computer and electrical engineering, as well as several mechanical aspects, is designed in order to provide 0-degree turning radius capabilities, lateral driving combined with standard vehicle motions, and anti-collision features. Utilizing these goals, the autonomous crab car comes to life using a Raspberry Pi for the brains of the vehicle, a LiDAR sensor for its eyes, and servo and DC motors attached to the mechanism wheels to provide transitability to the car. The autonomous crab car has been developed over the course of the fall 2023 semester and was completed to the current prototype at the end of November 2023. This car's design comes from the motivation of the team's eagerness to attack a challenge that encompasses our areas of engineering as well as mechanical engineering due to our future career hopes to work with the automotive industry or related systems. One key influence of our project is the Ionic Crab Walk, developed by Hyundai. Our project seeks to further the crab walk idea and develop an autonomous vehicle with limitless further applications. Now, let's meet the team. Our computer engineers are William Fye and Aidan Gowe. Will is from Fort Mill, South Carolina, and will commission as a second lieutenant this December. Will is going to Florida after graduation to begin his training as an electronics warfare officer utilizing parts of his computer engineering degree. Aidan is from Charleston, South Carolina, and will be working in the public sector for the Department of Defense after graduation. Aidan hopes to use his skills to develop cutting-edge technology and contribute to the advancement of society. Next, our electrical engineers are Richard Horry and Michael Keller. Richard is a student from Charleston, South Carolina, and is going to begin his career with Black & Veatch in the power industry. Richard has completed a co-op with Dominion Energy and an internship with Black & Veatch. Michael is a student from Triangle, Virginia, and is expected to commission as a second lieutenant this December. Along with electrical engineering, Michael currently studies animal and veterinary science and hopes to use his career to bridge the two rather different areas of study. The autonomous crab car was developed on two different fronts. The first was the hardware approach that began with a heavy emphasis on mechanical engineering along with electrical hardware. The second side of the project was developing proper software to integrate the motors with the LiDAR sensor, as well as a developed coordinate system used to control the vehicle. Now let's take a deeper look into the elements of the hardware of the car. The chassis is made of aluminum beams connected to one another using steel T-shaped brackets as well as corner joints to ensure the stability and strength of the design. This strong chassis is designed to support the weight of the 12-volt battery mounted using 3D printed connections, as well as the acrylic sheet that houses the other onboard components. The Raspberry Pi and the motor drivers are attached to the acrylic, preventing any potential parts from sliding. Also, atop this acrylic sheet are two 12-volt to 5-volt converters in order to step down the power supplied from the battery to the motors and the Pi. The two converters are required as a means to supply sufficient current to the Pi and the motors through separate tracks. Another element mounted to the top of this chassis is the LiDAR structure, which functions as the sight for the vehicle. The LiDAR sensor is mounted towards the rear of the car as a means to account for the blind spot of the sensor that is found within 0.25 meters. The height of the mount accounts for the blind spot and gives proper clearance to allow for the maximum range of the LiDAR of 9 meters and a field of view of 70 degrees by 55 degrees. Finally, attached to the front and rear aluminum beams of the chassis are the wheel structures. The wheel chassis are designed with two 3D printed parts connected using a Lazy Susan in order to allow for ease in turning of the servo motors. These motors, mounted in the upper chassis structure, are securely fastened to the lower wheel chassis as well as the main chassis of the vehicle.
Our design system has proven to be an excellent iteration of the deliverables discussed earlier today. The car performs to a high degree of accuracy and achieves a level of autonomy that is viable for our prototype. The vehicle has displayed several strengths, such as the car's reaction ability to obstacles and ability to evade collisions, the success in movement abilities and transitioning between lateral and standard driving, And finally, overall strength and physical design. The car has displayed some weaknesses that are mainly seen in the slight drift off of a straight path that occurs when the vehicle moves over large distances, as well as limited capabilities when the car encounters an obstacle while utilizing one of the coordinate system modes. The Raspberry Pi attached to the acrylic sheet is the computer of the car. The developed software downloaded on the Pi allows for control and autonomy of the vehicle itself. The software, developed in a bottom-up approach, is divided into 3 sections. The first is the LiDAR sensor that checks distances of objects in front of the sensor and returns no change in course until 10% of the pixels in front of the sensor return a distance of less than 0.8 meters. The second aspect of software design is developed into a coordinate system made up of 2 key variables, the XY coordinate system in millimeters and the angle of the car in degrees. The third piece to the software design comes in the car control, which is developed into 3 software structures. The DC motor encoder receives input signals to determine the direction of the motor. The DC motor controller is designed to control speed and direction direct the motor turn based on the desired movement, and when to turn off. The final aspect of software design comes in the servo controller, which converts the angle of the car to a PWM value and sets the PWM value to the servo motor. Utilizing the software integrated into the hardware of the car, the vehicle is able to function in several modes and transit using various methods. The vehicle is able to drive in a common orientation where the vehicle's wheels stay aligned and will move forward and back depending on the needs of the system. The second method is lateral driving, which transitions the wheels by 90 degrees to place them at the front and rear of the car. This mode allows for the car to move left or right while maintaining the forward orientation of the car. The final integrated method of movement is shown through the car's 0-degree turning ability, which is when the car stays in the same position but still completes a turn. The vehicle wheels stay oriented in lateral to the car, and the front and rear wheels turn in opposite directions to rotate the vehicle. These different movements allow the car to function in 3 different modes. The first mode utilizes the coordinate system where the car is given an input coordinate and drives to that location while maintaining a forward orientation. This uses lateral driving heavily. The second mode, developed, also uses the coordinate system. However, in this mode, the car calculates the best angle to take in order to quickly approach the input point. These first 2 modes use the LiDAR sensor to prevent collision and will halt the vehicle if an object is seen in the car's path. The final mode is an autonomous and continuous mode where the car continues on its path until an obstacle is encountered. When an object is seen, the vehicle will turn in 30-degree increments in the direction with most space available and will continue to turn until there is a clear path to continue forward motion. As a means to ensure the turn is able to occur, the car will first reverse about 1 foot to allow for proper clearance away from the object in the vehicle's path. These modes are accessed through a simple user interface where the user is asked if they first want to access the continuous mode, followed by which coordinate system mode they would prefer, before finally asking for input coordinates for the vehicle to move to. Our design system has proven to be an excellent iteration of the deliverables discussed earlier today. The car performs to a high degree of accuracy and achieves a level of autonomy that is viable for our prototype. The vehicle has displayed several strengths, such as the car's reaction ability to obstacles and ability to evade collisions, the success in movement abilities and transitioning between lateral and standard driving, and finally, overall strength and physical design. The car has displayed some weaknesses that are mainly seen in the slight drift off of a straight path that occurs when the vehicle moves over large distances, as well as limited capabilities when the car encounters an obstacle while utilizing one of the coordinate system modes. The autonomous crab car prototype was completed with several aspects that could use further development to improve the uses and capabilities of the car. Nevertheless, the car is one that our team hopes will allow for future innovations and use cases. Our team projects the autonomous vehicle's uses can range from simple things such as delivery of goods or various levels of mapping. The car would be an excellent technology to map simple things such as fence lines to ensure there are no holes or breaks, or in much more advanced projects such as mapping distant planets. Our team would like to thank Clemson University's Department of Electrical and Computer Engineering for our education within the program, as well as Dr. Hassan Raza for his continued help and guidance throughout the project. Finally, we would like to thank all those who have provided resources for our team's success in creating a functional prototype of an autonomous crab car.